we could really realize that there's features that we need in whatever setup that we've got in this room.
Yeah.
We're only going to know that by using it for a little while and understanding what manually is problematic for us to do.
Yeah, and I
So,
think there are some other things that we're also kind of learning about this. Like we know that the lights are going to be a little bit of like a setup issue. So like
yeah,
getting the stool and that type of stuff. But I also think it's going to be when the camera that we use for the board, how we're going to get that mounted,
yeah,
and all that type of stuff. I think it's all, um, and then where like how much remote control do we actually need?
yeah.
Because we can spend thousands of dollars on essentially a very fancy Stream Deck or
Linking the lights to everything.
yeah, and all that type of stuff.
Oh, hello. When did you walk in?
Yeah, I guess we should probably start talking about
What we're meant
what
to be
we're
talking about here.
Yeah,
Materials, iron and steel. So we're going to talk like a couple of basic properties here about
yeah,
iron and steel, and then we're going to talk about the very, very small, and then we're going to zoom back out to the large.
yeah,
Iron itself
yeah,
is a chemical element with the symbol Fe.
yeah,
So if you hear about non-ferrous metals versus ferrous metals, that's ferrous is what Fe is on that periodic table.
yeah. And iron was kind of like the first classified ferrous metal, so
Yeah.
it gets Fe as
Spoiler alert, it's a metal.
yeah. Spoiler alert: it's a metal.
And by mass, it is the most common element on Earth.
Yeah,
It has a melting point of 1811 degrees Kelvin, which is really freaking hot, 2800
yeah.
degrees Fahrenheit.
It's pretty spicy. 1,538 degrees Celsius for anybody who's on the Celsius.
Yeah.
On the
And
Celsius
and
system.
then obviously boiling point is like it does boil.
It does boil. You get anything hot enough, stuff will boil.
5,182 degrees Fahrenheit. I had a student ask me once, if you breathed in like iron steam,
That would not be good.
uh, whether it would poison you. I'm like, well,
It
the
would,
problem is that you'd be dead at that temperature.
yeah,
Like you'd be vaporized
long before.
long before it was really a problem for your lungs. This is
Yeah.
like,
Or your internal body chemistry. Like you would be carbon.
you would be, yeah, you'd
If
already
that.
be carbon. And then, like if you consider that,
You could make steel.
you would be a component of steel at
Yeah.
that point because steel is just a carbon alloy
Of iron.
of iron. So we're adding carbon to steel. All right. If we carry on to the next
Yeah.
one,
If I can, manage a slide deck to save my life.
which is why we were talking about that streamer deck earlier.
Yeah.
So
So I guess here, like, before we talk about steel, what is an alloy?
an
Like,
alloy is a mixture. It is essentially we melt two things and
We mix them
and
together.
We mix them together, and it becomes a new material, a mixture of that. So how do we create alloys? Is usually by melting them, although there are some solid state ways to do them.
Yeah.
But those are a lot more edge cases.
Yeah.
Most of the time, it's melt them,
Melting and mixing.
melting and mixing.
Yeah. And the purpose of alloys really is because we're looking to enhance the characteristics or properties of a material
Yeah,
in
and
some way.
and it's important when we're talking about material properties. Like, it's really easy to say like we're talking about good material properties,
Yeah.
and like to give some sort of value judgment to them. It depends on what you're doing.
Yeah.
And
The material properties themselves are neutral. It's the application that kind of like drives
Yeah.
whether or not a particular material property is desirable or undesirable.
yeah, it's either good for that application or it's bad for that application. But it doesn't mean that the properties themselves are bad.
Yeah,
They
and-
just are.
And like it doesn't mean that one material is better than another. It is again the application that you're trying
Yeah.
to use that material
There's tons of things that I would rather use a polymer for
for than a metal.
than a metal.
Yeah.
And it has to do with for that application,
Yeah. Exactly.
whether these are good properties for it.
Yeah.
You would often want to have something that stretches a lot if you're trying to hold up your pants.
Yes.
You wouldn't want steel cabling for a belt.
For a belt, would not make a particularly good belt.
It would be very uncomfortable.
It would be very uncomfortable.
So,
It would be very good at holding your pants up, though, if it was tensioned appropriately. But it would be extremely uncomfortable.
very uncomfortable. Yes. All right. Yes, steel belted. All right. An important thing to note, though, is that this mixing of things together can sometimes affect the melting point in and of itself.
Yeah.
So when we're dealing with these things, we're going to be dealing with a complex interaction of what happens when you mix two or more things together.
And I think it's also just as a side note, it is important to we're mixing materials to create a new material that is different than making something like plywood, which is a combination of wood and adhesives.
Yeah.
That is a different category of kind of mixing materials to enhance material properties, and we call those composites.
Yes.
But
they still the difference with composites is composites retain their original material properties.
Yeah.
It's just when you combine them together, they do things. We'll get into that.
We'll get into that, but
later.
it's important to understand. Here, when we say alloy, we mean we are making a new individual material from other materials.
Yeah, and alloys really only pertain to metals.
Yeah.
We call a similar mixture a copolymer in polymers.
Yeah.
So you're really only going to hear alloys as they relate to metals.
Yeah. We do something also very similar with ceramics to a certain degree, but that's it. We call those different things.
Yeah, there's different terminology in each one. So if you carry on to the next slide, before we really get into what happens when it's writ large on a melting pool of metal, we're going to start by talking about the very, very small, and then we'll zoom back out to the large. So, and that's because since we're dealing with alloys, the strength of materials are enhanced by allowing the solid structure to be formed of two interspersed phases.
Yeah.
And how we get there is we need to start by talking about the very, very small and then zooming out. But essentially what happens when you quench the alloy from a molten state to form these interspersed phases, you get specific material properties. And what's happening at each level of size, whether it's the atomic, the crystalline structure, the grain structure, each one of those adds a little bit more to the eventual material properties that you get.
And a lot of this comes down to essentially how the individual atoms of a material are arranged and how they behave at given temperatures. And then it's with steel, when we're quenching something, we're instigating very rapid temperature change.
Mm-hmm.
And that also has implications for these different kind of geometric arrangements that happen at the molecular or the atomic structure of a material.
Yeah.
And so the reason we're talking about this is that when you're looking at different materials and the materials that we make, we directly influence their atomic structure by going through these manufacturing processes, and they create the characteristics that we want out of a particular material.
Yeah. So let's carry on and look at some of these things. First, we have to talk about atoms in general, right?
Yeah.
Solid matter is held together by forces between neighboring atoms or molecules.
Yeah.
So these forces arise because of differences in the electron cloud. So you've got electrons that are orbiting. They don't follow a circular pattern.
It's not predictable.
It's not predictable, but they're going around and they're traveling really fast around a nucleus, which is essentially protons and neutrons.
Yeah.
So the electrons are the negatively charged, the protons are the positively charged, neutrons have no charge. The valence electrons, which are those in the outer shell, are the most
Perimeter electrons.
able to interact with each neighbors, and so how many are in that outer shell gives the kind of reactivity of that. And when you look at the periodic table, you'll see that things are organized in like in each column has a similar number of valence electrons.
And so periodic table is essentially organized kind of like by the, like, it's organized in a way, it's like how reactive is a material,
Yeah.
and what is its kind of not, I don't know what like, because you have the different types of materials too, right? You have like gases, you have solid metals, you have and then you have like
the noble gases. So the noble gases, like over there, neon, xenon, argon, all of those, like they're over there in that column because their outer shell is full.
Yeah.
Which means they have no space to react with other things. They don't like to react with other things.
It means they're very stable.
They're very stable.
You can't, but like that also means that they only like to exist as themselves.
Yeah.
You don't make new things out of them typically.
That's why they're called the noble gases, because they're stuck up.
Yeah. They're too snooty for the other elements.
They're too snooty for the other elements. So so the valence electrons really tell a lot of the tale. Like they're literally how the periodic table is organized.
Yeah.
And when a physical attraction between molecules or atoms is great, the material is held tightly together. Molecules and solids are bound very tightly together.
Yeah.
When the attractions are weaker, the substance may be in a liquid form and free to flow.
Yeah. So that would be water, like things like that. Anything you think of that would be a liquid,
Yeah.
is on the weaker end of this attraction.
Yes. Yeah. So that's basically what's happening, and this is across all materials. This is just how elements work.
Yeah.
So if you hit the next slide here, we need to talk a little about different types of bonds.
Yeah.
So ionic bonds, table salt is a good example of this, which is sodium chloride.
Yeah.
It's
interestingly enough, two of the most reactive things in the on the
periodic tables,
like come together and they form one of the most stable substances that does not change.
Because they give up all their reaction in that.
Yeah.
Right, and what they are is it's an ionic bond is where one or more electrons are wholly transferred from an atom to one element of the element of the other.
Yeah.
So like there's a
complete electron exchange.
Swap.
Yeah.
Yeah.
They swap electrons
To basically cancel out those things, and that's what happens is, like, you know, you've got one that has like an unstable amount of electrons as far as too many, and then one has too few, and then bam, ionic bond. Covalent bonds are where materials, electrons are shared.
Yeah.
They are neither, like, electrons are no longer are not solely around one nuclei. They are technically sharing around both.
Mm-hmm. And this would be, what would be a good material that has an example of a covalent bond?
Well, almost any polymer has, like thermoset polymers form covalent bonds. You know, like.
Is water a covalent bond? I don't remember.
Water is its own thing. It's a hydrogen bond.
Oh, that's right. That's right. Yeah.
But it's
that's different.
That's a little different. But like, I'm trying to think of a really common chemical that we would see that has.
We'll find one. We'll post it.
We'll post it. Yeah,
like
there's all kinds.
Yeah,
I'm just drawing a blank right now.
There are literally hundreds of materials.
You asked me for for an example, and I have none prepared.
Yeah.
Because today we're not talking about covalent bonds. We're talking about
metallic bonds.
metallic bonds, which is the next one. That's the one in bold.
Yeah.
And in metallic bonds, the atoms do not share or exchange electrons to bond together. Instead, many electrons are more or less free to migrate through a metal.
Yeah.
They're free floating, so that each electron can interact with many of the fixed fixed nuclei.
Which is important for a lot of material properties of metals that we find desirable from a engineering perspective.
Yeah. So, electrical conductivity wouldn't work if we weren't able to freely float electrons through something.
Which is why most metals are really good conductors.
Yes, absolutely. So, and that comes down all the way down to this. So, all material properties root and stem from the bonds
that are formed
between atoms.
And this is it's really, while we are not going to go hyper deep into how these bonds get formed and the physics behind them, it's really important that we keep in mind that we are always in this, every material that we interact with from an engineering perspective, it ultimately comes back down to what we're talking about here.
Yeah.
Every single time.
Every single time. And then you have molecular bonds, and this is when electrons of neutral atoms spend more time in one region of their orbit, and that basically creates a temporary weak charge there.
Yeah.
And this is sometimes called van der Waals or molecular bonds. They're very they're kind of weak.
Yeah.
And hydrogen bond is very similar to that. I mean, it is similar to that because hydrogen's only one proton, only one electron, so it's a little unstable.
Yeah.
It's a little wobbly in its orbit.
Yeah.
And so what happens there, and this is a hydrogen bond / a molecular bond, is what we see in water. Because it's that wobbly off-center thing, and that's what creates that angular structure to that the 120-degree angle that we see in a water molecule, the H2O, with the two hydrogen Mickey Mouse ears.
If you see it drawn out, the hydrogens explicitly exist at that 120 angle.
And that 120-degree angle is what gets us the basic repeating geometry that forms snowflakes.
Yeah.
And ice crystals.
Yeah, and that's why when you freeze water, it forms triangular sections as frequently as it does. It's because of that relationship.
Because of that angularity.
Yeah.
To that. So again, everything comes down to this level.
Yeah.
So I don't want to we're not going to go super deep into the physics of this, but it's important you understand there's a lot that is rooted off of this foundation.
Yeah, literally every material in the universe that we interact with, it's this level that derives their characteristics from it.
Yes. So here's an example of some things, an ionic bond where we've got all of the electrons basically migrating to one atom over the other.
Yeah.
And the covalent bond you see there, you see the atoms or the electrons being shared between individual ones. The metallic bond you see there, that has free-floating electrons in there. The molecular bond, you can see that it's really just kind of interlapping. They're not actually, that's not an intersection there. It's more like a Venn diagram intersection.
Yeah.
And it's really just to make up for that wobbly orbit. And hydrogen bond, this bond, you can see here, this is making that hexagonal structure due to the 120-degree angle of charges that are going in there. So that's the base structure that forms all of the things that go into a snowflake.
Yeah. Coming back to iron and steel, These atoms, when like as they exist as a solid, they get arranged into a three-dimensional array that we call a lattice. And a lattice is a common term that we use when we're looking at metallic materials in this way.
Yeah.
And so you will see this terminology
A lot.
a lot.
So lattice is just basically a regularly repeating configuration in all terms,
Yeah.
and that repeating relationship forms what we call a crystal. So that gives us our crystalline structure. So the difference between crystalline and non-crystalline is order,
Yeah.
right? It's like these are ordered repeating.
Yeah, they're ordered. It's an ordered repeating pattern that makes up like an atomic like the arrangement of atoms of a material.
Yeah.
Um,
And so we say something is crystalline when it's ordered, and we say something is non-crystalline or amorphous when it's not.
And this implies different material properties. Again,
Now, they could be the same atom.
it could be the same atom. It's important to understand that it is not.
And this is the thing.
Not all metals are always crystalline, and not all like water, for example, at
Yeah.
room temperature is non-crystalline.
Yeah,
When you freeze it, it crystallizes.
yeah. So like you can have, and it depends on that processing that we do of that material as to whether it forms a crystalline structure or a non-crystalline structure. So as we're going up, there's very little that we can do on the atomic level
Yeah.
to change
The behavior.
the behavior of it.
Because if you're at the atomic level, you're really dealing with like elements.
Yeah.
And elements, kind of by their definition.
The whole idea that like they were looking for the base elements,
You cannot separate them any further. And
But-
realistically.
But
so.
then as we get bigger and bigger from that super small, there are things that we can do to manipulate things and create a more crystalline structure, or create a certain type of crystalline structure, or create a non-crystalline structure.
Like these are things that we can now begin to influence to change the material properties of a material, or
Yeah.
to emphasize certain material properties and de-emphasize others.
Yes. So it's three-dimensional, right? We're only able on this slide deck to show you two-dimensional, but
understand it
yeah,
exists in three dimensions.
it exists in three dimensions. The forces of chemical bonding cause this repetition.
Yeah.
And it is a repeated pattern which gives control the properties like strength, ductility, density, conductivity, et cetera, et cetera. It controls a whole bunch of things, and the shape of it,
Yeah.
for that matter.
Yeah.
If you've seen a crystal, you're seeing writ large how each individual.
Yeah. And like when you for example, like when you're looking at if you look at like a natural crystal like amethyst or something like that, like the shapes that it takes are a direct representation of the crystalline lattice that is being. So when you see the different facets on like a natural crystal, that is the actual arrangement of those atoms.
Yes.
Like literally.
Yeah. So all metals have lattice structure.
Yeah.
That is a characteristic of metals.
Yeah.
So we keep that in mind. The most common basic crystal patterns associated with metals are body-centered cubic, face-centered cubic, and hexagonal close-packed. We'll kind of show you each of these individually, so let's get onto the visuals on those. So when we're looking at these, it's important to get an idea that these are just representations. Obviously it isn't like things aren't made up of balls and sticks.
Yeah.
They're made up of strings, as we all know.
Yeah. Everything is a string.
No, these are models, right? Yeah. And it's important to keep in mind that when we talk about these things, these are just models. And we draw a lot of space in there so that we can see what's going on. Yeah. And it is when if we were actually to look at these things, it would look a little different. And we'll see some better models for the spatial relationships to things. But the important thing here when we look at these, body-centered cubic has a molecule, an atom in the middle,
Yeah.
and then a cubic,
Yeah.
right? And then face-centered cubic, instead of having that atom in the middle, it has atoms on each of the faces.
Yeah. So, like, if you think of a cube, you have 4 points that define the square, and then there is, on that same plane, there is one exactly in the middle.
Yes. And then hexagonal close packed is a bit of the close pack part of it is that sandwich structure.
Yeah.
So we have a hexagon with an atom in the middle, on the bottom, and the top making up the bread of this sandwich, and then taking up that space in between, which makes it close packed,
Yeah.
is a little triangle of additional atoms.
Yeah.
You can also have simple cubic, but you can see the differences there between body-centered and face-centered. So let's go ahead and hit the next slide. So these models tell you a little bit more about what's going on here, particularly when we get to the one on the left there.
Yeah.
So this is for body-centered cubic, and you'll see that it's got essentially an eighth chunk of 8 different atoms there.
Centered on one atom.
Centered on one atom, and this forms basically the base unit, the repeating unit on there. So if we were to define this, it's easy to just draw whole spheres, but when we want to talk about what's actually repeating at its most simple level, it look like our repeating pattern is actually what's made up there, and it's basically showing the sections of its neighbors.
Right.
And when we look at this, without the lines and without all that extra space in there, you can kind of see like these are a bunch of balls that are, and they're not actually balls.
Yeah.
But
the sphere kind of represents the perimeter of that electron field.
Yes.
And so, like, what this is really depicting is we have atoms that are in close proximity to each other, and the points of intersection is where the electron fields interact.
Yeah. So, so this is what that looks like. So we take a bunch of repetitions of that fundamental repetition unit, and we get ourselves a stack like you see in the middle of this slide.
Yeah. So, like, if we're looking right around here, this is kind of what the beginnings of a crystalline structure look like at the atomic level.
At the atomic level, and it's look like,
yeah,
but it's better representation than the stick and ball in lots of space. We do that as kind of an exploded view. You can think of it almost like an exploded view on a CAD drawing.
Yeah.
So, and then here we have a face-centered cubic, and so here we have half spheres on 6 sides, and then we have 8 spheres on each of the corners.
Yeah.
And you'll see that it forms another stack here, over there, that looks a little different.
Yeah.
When we start repeating that over and over and over again. It's important to understand that if we think about it, we add all of these together, right? We've got essentially this base unit here consists of, if we add all the fractions together, we've got 8 eighths.
Yeah.
So that's 1.
Yeah.
And then we've got 6 halves.
Which would be 3.
Which would be 3. So this unit is comprised of, if we look at the whole picture, essentially 4.
Yeah.
3 plus 1.
Yeah.
I think I can do that.
Yeah, 3 plus 1.
3 plus 1.
I was mathing on the eighths incorrectly.
3 plus 1, and that's 4.
Yeah.
And so this has 4. The other one had 2.
Yeah.
If we added all of those fractions together. So
Yeah.
like, although these are drawn the same, they're not drawn to scale. Because if you can have a material that is both, is capable of being both face-centered and body-centered.
And body-centered, yeah.
And if we go back to the previous slide here, You'll notice we put down chromium,
Iron,
and tungsten.
tungsten. W is tungsten, FYI.
For obvious
Obvious
reasons.
Yeah. Like obviously it's tungsten.
Go to the next one, and then we've got
Copper.
copper, we've got aluminum, we've got
Gold.
silver and gold.
Yeah.
But you can also get iron in face center cubic.
Yeah.
So it can and that's one of the beautiful things about it, and we're going to get into this later on.
So we've looked at these two patterns. What does characteristically what's the difference between them?
Yeah. So let's shift back and forth.
Yeah.
Look at the orderliness of this, and look at the orderliness of this one. So if you look at it, it's a lot more packed in together in a much more. So this one seems a little looser.
Yeah.
And if you go to the other one, that seems tighter, and it seems kind of jumbled in a way that you almost can't perceive there. And and we'll get into the material properties as they relate to these different phases when it comes to steel and other things. But it's going to affect.
This is a physically different structure.
Yeah.
And that's going to have implications for how the material behaves.
Yeah, and there's something called slip planes, which is where, and this leads to ductility.
Yeah.
If you look at this one versus the other one, this one is actually this crystalline structure has slip planes, where if you think of these balls as balls, they're able to roll past each other in certain directions.
Right.
Right, and that leads to ductility.
Yeah.
So.
Exactly, a little close packed.
So this one, the unit cell consists of 3 layers of atoms. You've got that triangle in the middle, and you've got the hexagons with the center atom on the top and bottom representing this. So metals that are this way are magnesium, titanium, zinc.
And I think the other thing that would be important to point out here is that it's not what we're pointing at here, the elements that we're calling out here, that's not the exhaustive list of all the elements that can assume this
formation. Yeah,
formation.
It's just the typicals.
These are the typical ones.
So there you go.
Yeah. I think another one that can do this is, I think carbon does this. Is that correct? When you form graphite? Or is that technically a different? Is that a different form?
I don't remember.
Don't quote me on any of this.
Actually, I'm going to make a pause.